Self-driving cars are awesome, but learning how to make one with a full-size car can be tricky. To avoid this, many groups spend at least part of their time working on smaller-scale vehicles. Georgia Tech's Auto Rally project, for example, has been able to push the limits of how expertly a computer can control a car by working with a scale platform robust enough to crash, flipping end over end without even needing a reboot to get going again. In this video, I'm going to show you how you can put together a small and inexpensive self-driving car with enough power to start exploring how these vehicles actually work, and enough extendability to eventually get into some of the latest research. I'm going to build my autonomous car by modifying a remote-controlled toy car, so the first step is to find a car to buy. Any RC car will do generally. The most important thing to look for is an independent receiver. Many cheap RC cars now come with a combination receiver and motor controller, but this doesn't give us any way to control the car from a computer without replacing the entire motor controller. Cars that have separate receivers and motor controllers use 3-wire PWM cables to connect them. We'll be plugging these cables into our computer instead of the receiver, so it's important to find a car that actually has these cables. For my build, I've chosen this Turnigy 1/18th scale mini stadium truck. It's big enough to carry the computer I'm using, and has an impressively powerful brushless motor inside. And the pictures on the product page clearly show that all-important independent receiver. I'll also grab a battery charger, and LiPo safety monitor for the car. The safety monitor warns us before we accidentally drain the battery to a dangerously low level. Now that you have an RC car selected, it's time to remove all the bits you won't be using. For the Turnigy Stadium truck, I removed the body cover and the receiver. This is also a good time to go ahead and install your car's battery, so you don't forget to leave space for it as you plan your modifications. To make our car smart, we're going to use the ever-popular Raspberry Pi. The standard Raspberry Pi camera will give our car a way to see the world around it. And while the Pi itself isn't very good at controlling motors, we can use Adafruit's PWM hat to give us an interface for the car without a bunch of custom electronics. I also picked up a portable USB battery pack to run the Pi without plugging it into the wall. To attach the Raspberry Pi and camera to the car, we need a few custom parts. If you're also using the Turnigy Stadium truck, you can grab the models I used from the link in the description. If not, you'll have to design some of your own. There are a lot of ways to go about designing your custom parts. Free software like Autodesk Fusion or Blender will let you model the parts on your computer. If you don't have access to a 3D printer at home or through a local makerspace, services like Shapeways or 3D Hubs will print your models and mail them to you. And never underestimate the supplies you can get from your local craft store. A bit of balsa wood and zip ties can go a long way. I designed my parts to fit over the shallow rim of the Turnigy truck's chassis. My personal printer has a small build area, so I designed everything in small parts that would fit on my printer and then be screwed together. My models also use screw holes sized for forming taps, so I can put the screws in right away without having to use a proper tap to make the threads. The screws will deform the plastic to make their own threads the first time you screw them in. With the designs ready, it's time to print the parts, attach the Pi and PWM hat to the 3D printed parts, and attach the whole assembly to the car's chassis. Be careful when screwing everything in, because it can be easy to strip or crack the 3D printed parts if you over-tighten the screws. Plug the steering servo PWM cable into channel 0, and the motor controller PWM cable into channel 1. You would normally need to use an external power supply here to power the motors and servos. In this case, the car's motor controller provides power on the red wire that will go through our PWM board to power the steering servo as well. With the parts screwed together, battery pack zip tied in, and everything mounted to the car, we're ready to start making it drive itself with some code. To give an example of an easy self-driving demo we can do with this car, I've set up a simple track on the floor with some orange cones. We'll use some basic computer vision techniques to get the car to drive around this circuit. To begin, we'll need to make sure our Raspberry Pi is set up correctly to work with the hardware we've got on our car. If you're new to using the Raspberry Pi, follow the official tutorials for installing Raspbian using the Noob's operating system installer. Once that's set up, we need to enable some modules using the configuration tool. Select Raspberry Pi Configuration from the Preferences menu. On the Interfaces tab, enable Camera and I2C. Press OK and reboot the Pi so that the new modules will load up. You can test the camera using the raspi still command. Our code will use 3 libraries. RaspiCam will let us get camera images in C++. If you're using Python, use PyCamera. OpenCV will let us understand the images to make smart choices about how to drive. And PyPCA9685 will give us control over the PWM hat from either C++ or Python. Installation instructions for these libraries are on the project page on my site. Now it's time to write some code. I'll start by making a simple CMake project. It'll be called racecar code, define a single executable, also called racecar code, and link against the 3 libraries I'll be using. Our actual C++ code will all be written in main.cpp, which starts just by including the headers for our libraries. Unistud.h gives us access to the uSleep function, and iostream lets us send text to the screen. The main method starts by declaring some useful constants and initializing our hardware. I've set the resolution of the camera to 320 by 240. This is small so that we can process the entire image quickly. I've also set the PWM frequency to 60 Hz to match what our motor controller is expecting. Next, I'll ask OpenCV to create a preview window and declare a variable for holding the raw camera image called frame. This gets us to the main loop of our code. Our code will repeat for as long as the camera has images for us or until we press the spacebar. Inside the loop, we fill frame with the image using camera.retrieve and show that image in our preview window with imshow. To make our car move, we need to actually send some PWM commands to the motors. The PCA library lets us do this by specifying the on time of the PWM square wave in milliseconds. For the Turnigy truck motor, 1.7 milliseconds means stop, and 1.76 milliseconds gets us moving at about 20% our max speed. We have to hold the signal at the stopped value for 1 second to give the car's motor controller time to enable itself. After our main loop, we'll throw in a line to stop the car so it doesn't run away from us. Now for the hardest part. How do we decide what direction to go based on what the camera sees? Since the boundaries of the test course are made of orange cones, let's see how far we can get just by paying attention to the color orange. That can actually be pretty tricky to do with the image the camera gives us. See, when we ask the camera for a new frame, it encodes the colors in the image using the BGR color space. This means for each pixel in the image, there are 3 values or channels that control the color: blue, green, and red. By adjusting these channels, we can produce nearly every possible color, but it can be tricky to define simple rules that isolate one color, like orange, from the others. Luckily for us, BGR is not the only color space that we can use. One color space much more common for color matching is called HSV. Again, there are 3 channels, but this time they represent the hue, saturation, and value components of the color. While BGR forms a cube of possible colors, HSV represents a cylinder, and we can pick a slice of this cylinder with some very simple thresholding. In our code, we're going to use 2 variables to define the orange slice of HSV. We'll say that orange is any color where the hue channel is between 0 and 20, and the other 2 channels are between 100 and 255. The hue filter actually picks the color. The thresholding on the other 2 channels prevents us from including dark or low saturation colors like gray or black. Next, we declare 2 more image variables for holding the HSV version of our image and the thresholded image. ConvertColor fills frame HSV with the HSV version of our original image. And InRange does the thresholding for us. Any pixel whose color is in the range we picked gets set to 255 in the output image. If the color is outside our range, the output is set to 0. This lets our car identify the obstacles on the track, but we still haven't made any decisions on where to drive. To keep things simple, let's only pick between turning hard left, turning hard right, or driving straight. Since we're only trying to make that decision, we can drive towards the section of the image with the least orange pixels, left, right, or center. These sections of the image are called regions of interest, or ROI. We can define them in code using OpenCV's rect object and dividing our image width into thirds. Then we pack these regions into an array and make a second array with the PWM values used to turn left, straight, or right. A third array, non-zero counts, gives us a workspace to save how many orange pixels we found in each of the regions. The standard library gives us a function called transform. which fills an output array by calling a function on each element of the input array. In our case, the input array is the array of regions, and the output is the array of non-zero counts for each region. The last argument is the function that actually counts the non-zero pixels in a region, which we'll declare as a lambda immediately above our call to transform. It will capture the thresholded image and take a single parameter to define the region. Then it just has to return the result of OpenCV's count non-zero applied to that region of the thresholded image. At this point, non-zero counts tells us how many orange pixels were in each region of the original frame. Since we want to steer towards the region with the fewest obstacles, we'll use the standard library's min element to pick the smallest element from non-zero counts, and distance to get the index of that element. Because all of our arrays are in the same order, we can use this index to draw the selected region on the previewed image and send the chosen PWM value out to the steering servo. And that's all the code. Back in the terminal, we can build our CMake project, turn on the car, and run our program. The code will keep running after we unplug the screen, so our car can drive untethered around the track. You can extend this simple approach in a lot of ways. More regions could give the car finer control. You could bias the car towards certain directions by adjusting the non-zero counts array, because maybe you're in a drag race where turning is less likely. And you can avoid obstacles of different colors by running multiple in-range thresholds over the image and combining their results. You can even stack extra Raspberry Pi hats to add special processors for things the Pi can't handle on its own. While simple, our code gets the car driving around this test track, and variations of this approach have won some collegiate autonomous car competitions, so it's not a bad start to a self-driving car. Detailed instructions about everything I did in this project are available on my site. Check out the link in the description. And if you see the code from this video and think, that's way too simple, no real car could run on that, go check out the Welch Labs channel, which just started a new series on how autonomous cars work. His first video talks about how the earliest self-driving vehicles used very similar color matching to pick out the road pixels from the image. He's an expert on the subject and has implemented his own novel techniques to get real cars driving on real roads, so you'll learn a lot. And of course, thanks for watching.